This video is on partial orderings and their properties. So a partial ordering or partial order is a special type of relation, and we've been dealing with relations. This one doesn't have to relate every element to every other, but it does have to have three properties. The relation R, in order to be a partial order, needs to be reflexive, antisymmetric, and transitive. If R is reflexive, antisymmetric, and transitive, then it's known as a partial order on a set S, or we can just say an order. Let's remind ourselves what it means to be reflexive. For reflexive, we want for every element in the set, we need it to be related to itself. So if you were to look at the connectivity matrix, you would want all ones down the main diagonal. Antisymmetric. Different ways that we could write this, but I like to say for A not equal to B, so I don't worry about that main diagonal. For A not equal to B, if A is related to B, then B cannot be related to A. And another thing you could say is, if you'd rather show that if you do have A related to B and you have B related to A, then that can only mean that A does equal B. So again, I'm just going to verify it with that first property. If you looked at the connectivity matrix for antisymmetric, you don't worry about the main diagonal. They can be ones or zeros. But again, for our order relation, we are going to want this to be reflexive. So we are going to want ones down the main diagonal. And you don't want symmetrically placed ones. So if you have a 1 in this position, then you don't want the flip of that. So you do not want a symmetrically placed 1. I'll take that away. You're going to want a 0 there. It's okay, though, to have 0 symmetrically placed because that means there's no relation for A and B there. But again, no symmetrically placed ones. Transitive, this means for A related to B and B related to C, we get back A is related to C. If you looked at the connectivity matrix, you're going to take the Boolean square of this, which you can write different ways. It's the composition function here. And that needs to be less than or equal to the original connectivity matrix. So what that's saying is when you do the composition R of R, it will be a subset of your relation. So it'll remain in the relation, so that means it's going to be transitive. So those are the three properties that we will be checking for R to be a partial ordering. And in the next video, we'll just look at each individually. We'll take an example of the partially ordered set of the integers with the less than or equal to. So again, you can see why these are all important for it to be reflexive, antisymmetric, and transitive. It gives us a nice ordering. Like, let me just use -3, -2, -1, 0. So every element is related to itself. So we have reflexive. And then antisymmetric, that's important because I know that -2 should precede -1 when I'm talking about this ordering. -2 is less than or equal to -1. I know which one needs to precede the other. So it couldn't not be symmetric. That would be bad because then you'd have -1 is related to -2 and -2 is related to -1. I wouldn't know which one precedes the other. And then transitive gives us this nice kind of chain, this nice property where I go from one to the next to the next. So I have this ordering from a preceding element to the next element to the next element.